Welcome to 5.5 Day 1, Double Angle and Power Reducing Identities. Today's objectives are to use double angle and power reducing identities to evaluate trigonometric expressions and solve equations. So here are the double angle identities. You'll notice that we have sine of 2 theta is the same as 2 sine theta cosine theta. Tangent of 2 theta is the same as 2 tangent thetas over 1 minus tangent squared theta. And then for cosine 2 theta, we actually have 3 different options. And we look for the option that's going to work best in the equation or expression we're working with. The top identity is actually found from using the cosine sum identity. That's where that comes from. And the other bottom 2 are just rewrites of the top one, using our Pythagorean identities to switch things out. On the bottom here is the proof for sine of 2 theta. For the double angle, on the bottom there is a proof for the double angle identity for sine 2 theta, or you're using the sum identity, and you have sine of theta plus theta, and that's how that identity comes around. All right, so we're going to use these identities today to help solve equations and simplify expressions. We want to evaluate expressions involving double angles. If sine of theta is 3/4 on the interval from 0 to pi halves, find the sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. What we end up doing is using that sine of theta is 3/4. We're going to use that to draw a triangle and then find out what our tangent and cosine functions of that are. And then we'll use those to help find our double angles. You notice we are in the first quadrant for our interval. So if we draw a triangle, it'll be in the first quadrant. Here's my theta. This would be 3. This will be 4. We will need to find what x is. And so we have x squared plus 3 squared equals 4 squared. Using our Pythagorean theorem, we end up getting x squared. 3 squared is 9, 4 squared is 16. We get 9 is 16. Subtract it off, we get x squared equals 7. And the square root of this is that x equals the square root of 7. We can now use this to find our cosine and tangent. So cosine of theta is just the square root of 7 over the hypotenuse of 4. The tangent of theta is sine over cosine. And sine is 3/4. Cosine is the square root of 7 over 4. The 4's end up canceling out, and you're left with 3 over the square root of 7. We would rationalize the denominator, and this is 3 square root 7 over 7. That's my tangent. So we found cosine and tangent. Now we're just going to use our double angled identities from our sheets to find sine 2 theta, cosine 2 theta, and tangent 2 theta. So if you look at your sheet, the sine of 2 theta is the same as 2 times sine theta, cosine theta. We know what our sine of theta and cosine of theta are, so we can just plug them in. The sine of theta we know is 3/4. The cosine of theta we know is square root of 7 over 4. And then we just simplify this. We have 2 times 3, which is 6. 6 square roots of 7 over 16. Trying to save some room here so we can make sure we fit everything. And this will simplify down to 3 square root 7 over 8. That is my double angle for sine. So sine of 2 theta is 3 square roots of 7 over 8. We do the same thing now for cosine. We'll use our identities. So for cosine of 2 theta, if you look at your sheet, we have 3 options. I think the easiest one to use today is going to be the cosine squared theta minus sine squared theta. We have cosine squared theta minus sine squared theta. We plug them in. Cosine squared is the square root of 7 over 4 squared minus the 3/4 squared. When we do this, we get 7/16 minus 9/16, which is negative 2/16, which simplifies to negative 1/8. All right, so we found our first two. Now we have to do tangent. And there's two different ways to do this. You could just take your sine of 2 theta over your cosine of 2 theta. Do it that way. That's one way. It's probably the easiest way. So let's do it that way. You could also use your tangent double angle identity and use your double angle for tangent for this. The easiest one to use in this case is going to be tangent of 2 theta is equal to, and we're just going to use the sine of 2 theta over cosine of 2 theta. So 3 square root 7 over 8 over negative 1/8. Division by a fraction is the same as multiplying by the reciprocal. So this is 3 square root of 7 over 8 times negative 8, which becomes negative 3 square root 7. That's my tangent of 2 theta. So I have solved for all three. This is my tangent 2 theta. The green here, that's tangent here. The green was my cosine of 2 theta. And the top was my sine of 2 theta. So we have solved for all three. So that is finding double angles. You do have a few of these on your homework today. Next thing we're going to do is solve an equation using double angle identities. So we have cosine of 2 theta minus cosine of theta equals 2 on the interval from 0 to 2 pi. We have a double angle in here. We're going to go right to our double angle identities and use one of them. And again, we're going to look at the one we think is going to work best for us. And if you look at your double angles, we have a couple of options. We can use any of them. I don't want to introduce a sign into this if I don't have to. So we don't want to use the first one or the bottom one. We want to keep everything in terms of cosines if possible. It makes our math easier. So I'm going to use the middle one. So cosine of 2 theta turns into 2 cosine squared theta minus 1. Then we have minus cosine theta equals 2. And now it's just an equation we have to solve. We'll bring the 2 over. And I'm going to rewrite it so I put it in order so it's in standard form for a quadratic. We have 2 cosine squared thetas minus cosine theta minus 3 equals 0. We have to do the AC split. Unless you know how to do it with guess and check, 2 times negative 3 is negative 6. I will show you the AC split. What factors of negative 6 will add to negative 1 if I have a negative 3 cosine theta plus 2 cosine theta. So we did our split, we group, and we factor. Out of the first group, I can pull out a cosine theta. Leaves behind 2 cosine theta minus 3. Last one, I can pull out a plus 1. We get 2 cosine theta minus 3. So our factors are cosine theta plus 1, 2 cosine theta minus 3. Set the factors equal to 0. So we have cosine theta plus 1 equals 0. So we have 2 cosine theta minus 3 equals 0. And we solve both. I run out of room on the bottom, so I'm going to go up to the top here. All right, so the first one, we have cosine of theta plus 1 equals 0, and I'm going to change that and move the 1 over to the other side. So like cosine theta equals -1. The other one I'm going to start by moving the -3 over. So I got 2 cosine theta equals 3, and cosine theta then equals 3/2. All right, so we look at our two things. We solve for cosine theta. We want to find out what theta is. On the unit circle, cosine theta equals -1 at pi. Cosine theta equals 3/2, never on the unit circle. So this isn't possible on our unit circle, so we can't use that side. The only answer we have is that theta is pi. And again, just like we did the other day when we were solving equations, we introduced a squared term into our equation where there wasn't one before, so we got extraneous solutions or extraneous possibilities that didn't work. And that does often happen when we introduce squareds into stuff that does not have squareds, into equations. All right, so that's that one. Next, we're going to move on and look at power reducing. Here we have power reducing identities. We don't always want to have to deal with stuff that has powers in it. Sometimes it's easier to work with things without exponents. So we do have these things called power reducing identities where we can change sine squared theta into 1 minus cosine 2 theta over 2. We can change cosine squared theta into 1 plus cosine 2 theta over 2. And tangent squared theta can be turned into 1 minus cosine 2 theta and over 1 plus cosine 2 theta. The proof for this is down below. This can become an involved process, especially with one like this. It says use an identity to reduce a power. So we want to rewrite cosecant to the 4th theta, and we want to write it in terms of cosines of multiple angles with no power greater than 1. So we want to get rid of all the exponents when we're done, and we want to have everything in terms of cosines. So we have nothing to do right now with cosecant to the 4th, so we need to rewrite this in a way we can use it. So like I said, this is going to be a little bit involved. So this is the same as cosecant squared theta, all squared. All right, and cosecant is the same as 1 over sine. So cosecant squared is the same as 1 over sine squared. Theta, all squared. Now we're going to start changing things into cosines because we want everything in cosines. So this is the same as using a Pythagorean identity, 1 minus cosine squared theta, all squared. Now we start using our power reducing. And we have on our thing what cosine squared becomes. We are going to be coming and getting some very complex fractions. This is 1 minus cosine squared becomes 1 plus cosine 2 theta over 2. And this is still all squared. We want to get a common denominator on the bottom. So what I'm going to do is, to get 1, have the same denominator, you're going to have 2 over 2 is the same as 1. So this part right here becomes, let's see if I can show you this. That 1 becomes 2 over 2. Then we have a common denominator we can combine. We have 2 minus 1, which is 1. So we have 1 in the top. Then we have 1 minus cosine 2 theta over 2 all squared. All right, when you are dividing by 2 like this, we have 1 divided by 1 minus cosine 2 theta over 2. We want to get rid of this complex fraction. So if we multiply top and bottom by 2, so if we multiply this, technically inside the parentheses by 2 over 2, what happens is the top becomes 2. The bottom, when you do this, just becomes 1 minus cosine 2 theta. We basically have wiped out this bottom fraction by doing this. So we multiply top and bottom by 2. The 2's on the bottom cancel out, leaving just the 1 minus cosine 2 theta. The top is 2 times 1, which is 2. This is still, we did this all inside the parentheses, it's squared. And this is rather difficult algebra. Now we bring that square in, and we're going to square the numerator and square the denominator. The numerator becomes 4. The denominator, when you square 1 minus cosine 2 theta, becomes 1 minus 2 cosine 2 thetas minus or plus cosine squared 2 theta. So we have 1 minus 2 cosine 2 thetas plus cosine squared 2 theta. I'm going to put this one in parentheses because it's getting a little bit crazy here so you can see what's going on. We have a square then still, and it says we want to get rid of the powers, so we have to get rid of the powers, again, by using a power reducing. So we have 1 minus 2 cosine 2 thetas. We have to do the power reducing again. This is, like I said, this is like the hardest problem you'd see. And what's tricky with this one is the cosine squared is, like we showed earlier, that 1 plus cosine 2 theta. So we have to multiply the argument by 2, and this becomes 1 plus cosine 4 theta over 2. So we have this, again, complex fraction. Let's get this all have the same denominator on the bottom. So I need to multiply these first two terms by 2 to get them have the same denominator. That way you get 1 over 2 is 1. To get 1 to have the same denominator, it'd be 2 over 2. To get negative 2 cosine 2 theta to have a denominator of 2, it becomes negative 4 cosine 2 theta. All right, so we have our 4 in the numerator, and our large denominator, we have to multiply the 1 by 2, we get 2. We have to multiply the negative 2 cosine 2 theta by 2 to get negative 4 cosine 2 theta. This is because we're getting that common denominator, plus 1 over plus 1 plus cosine 4 thetas all over 2. We got a common denominator in the bottom. Now we need to do the same thing we did earlier. We are going to get rid of our complex fraction by multiplying the numerator and our large denominator by 2 over 2. That cancels these two out. This leaves 8 in the numerator. Our denominator is still really large. I'm going to write it in order, standard form. So I have cosine 4 theta minus 4 cosine 2 theta plus 3. And that is reduced. We no longer have any powers of 2. Everything's in terms of cosine. That's as far as we can take it. This is probably the most difficult type problem you would see. You're not going to have too many of these like this. It is a lot of algebra. I'm going to try to keep most of them to just 1 power reducing. We got to apply it 2 times in this one. But it shows you what we have to do algebraically with our trig. All right, last one, we have solve sine squared theta plus cosine 2 theta minus cosine theta. We want to solve the equation using a power reducing identity. We have sine squared right now. We want to get rid of the sine squared. We have to reduce the power. We look at our list and we find out sine squared theta is the same as 1 minus cosine 2 theta over 2. And then we have plus cosine 2 theta minus cosine theta equals 0. So I don't want to work with fractions. So what I'm going to do is I'm going to multiply every term by 2. And if we do that, we get 1 minus cosine 2 theta plus 2 cosine 2 theta minus 2 cosine theta. And we multiply 0 by 2, we get 0. So what I did is I took this whole thing here and multiplied every term by 2. That's that least common denominator method we learned a long time ago. Now we look at what we have and we combine like terms. We have a negative cosine 2 theta and a positive 2 cosine thetas. We have a negative cosine 2 theta and a positive 2 cosine 2 thetas. So they become a cosine of 2 thetas, positive, minus 2 cosine theta. This is equal to 0. we want to get rid of this double angle because we need to get it in terms of theta to do this, to solve it. And our cosine of 2 theta, again, we want to get something that only has cosines in it if possible. Make things easier, so we're going to use that 2 cosine squared theta minus 1. So our cosine 2 theta becomes 2 cosine squared theta minus 1. We still have the minus 2 cosine thetas at the end. I'm going to put this in standard form so it's easier to see how to factor it. We have 2 cosine squared thetas minus 2 cosine thetas equal to 0. Factor out 2 cosine thetas. We're left with cosine theta minus 1. Set each factor equal to 0. So now we have 2 cosine theta equal to 0. We have cosine theta minus 1 equals 0. So when we solve both, we get cosine of theta equals 0. When you divide by 2, 0 divided by 2 is still 0. And we get cosine of theta equals 1. For the first one, this happens at pi halves and 3 pi halves. And for cosine of theta equal 1, this happens at 0 degrees. Now, with this one, it did not give us an interval, so we have to go back to what we did earlier this chapter and write them all down. So our thetas are equal to 0 plus 2n pi halves plus 2n pi, 3 pi halves plus 2n pi, and don't forget that n is an element of the integers. This is my answer right here. So don't forget that when we don't have an interval or it doesn't say what quadrant to work in, we do need to give those answers in terms of pi and how many times it happens every time it goes around a circle. That was solving the equation using a power reducing identity. All right, so that's it for 5.5 day 1. Today we looked at using double angle identities and power reducing identities. Make sure you're showing your work. Thank you for watching and have a nice day.